Uh, Hello, this is Eric. So today we're going to talk about how to use AbstractQueuedSynchronizer to build a simple mutex, and we'll analyze how AQS implemented the acquire and release methods. So first of all, I assume everyone knows what a mutex is. So there are two methods, lock and unlock. So in the lock method, we notice that we are calling AQS acquire method. In the unlock, we call release method. This is a bare minimum version of a mutex. It's very simple. There's a helper class called sync, which extends AQS, where we override two methods: tryAcquire, tryRelease. In the constructor, we set the original state to be 100, which means unlocked. Actually, this can be any number. The original state is unlocked state by default. So if you set this to 200, 300 is up to you. In the tryAcquire, then we compare the state. We use the compare and the set state methods in the AQS. So to see if it's 100 or not. If it's 100, which means it's unlocked, we change the number to 1 or to whatever the number you want, means unlocked, means it's already locked. We've taken the lock, we change the state. In the release, we change the state back to be 100. So here we have a look. When we call lock, we call the acquire method. So what does the acquire method do? First, it calls our method tryAcquire. As we've said, if the original state is 100, we change the state to 1, then this will return to true. When we return true, well, basically, you will get out of this if statement and you acquire the lock. Lucky you. And what if some other thread, let's say thread A, has already required a lock? We are thread B. Well, thread B comes in, have a look, this returns false, and then the method acquire queued will be executed. And before that, we'll call addWaiter. So what does addWaiter do? So the command says creates an in-queues node for current thread and given mode. So in AQS, AbstractQueuedSynchronizer, it keeps a linked list, double linked list, and as a way to manage the threads. So we can have a look. So the linked list looks something like this. There's head, and there's nodes. Let's say node 0, and the node has a reference to your thread, which it can park your thread or unpark your thread, dequeue your thread, enqueue your thread. So that's basically how it works. That's the basically internal data structure. So addWaiter will create a new node with your thread. And basically return the node. This is a simple, fast approach. If this is not successful, we call enqueue. This is an interesting method. So here we see the spinning action. Basically, the core logic lays in compare and set tail. Basically there's a head, there's a tail of the double linked list, which are kept by AQS. And this is using the compare and swap method in unsafe class in JDK, which is an atomic operation and guaranteed by operating systems, sometimes supported by hardware. And basically what this does is I try to enqueue the thread to the tail. If in the meantime some other thread comes in, jumps in and enqueue their node into the tail, basically this method will fail, but since we are spinning, we'll come back again and basically add our node to the tail until it succeeds. This is pretty simple, pretty classic implementation addWaiter. But does it mean what happens after we add our thread, enqueue our thread? Do we park the thread? Not necessarily. So there's a smart design by Doug Lea here, and each node has a status called wait status. We can have a look. Node that each node has a so each node has a wait status. This is a flag. Usually the wait status of the previous predecessor determines whether determines the successor should be parked or unparked. And by doing this, you know, parking and unparking operations are expensive. So by keep updating the flag, sometimes we may avoid unnecessary parking and unparking. For example, if a thread is ready to be parked, we basically update the wait status to be signaled. But in the meantime, if another thread, which let's say thread A, which had held the lock, just finished work and returned the lock and update the wait status to be 0, then we don't really need to park this thread. Then we check it again, it's 0, then we are good to go. So we avoid parking unnecessary parking and unparking operations. As a result, the performance is improved. So let's go back to where we were. So at this stage, we have added the node to our queue. Let's have a look at this acquire queue method, where we notice there's a spin operation here. If you fail normally, so one lucky scenario is our thread is queued, just queued in the queue, but the thread A, which has held the lock, finishes work and releases the queue, and we call the tryAcquire method. It actually returns true. In this case, we actually don't need to park the thread, and the thread is good to go. So basically, we update the head. What it does is basically pointing the head to our new node and nullify the references. So this becomes a new head, new dummy head. And then we can get rid of the old one. All the new node that's come in and queued up will be queued up after our new head. This is what it does. Okay, let's go back. So this is one of the lucky case. What if usually if thread A is holding the lock and doing some work, we fail to acquire the lock. Basically, we come here, check the signal. Basically, it's the signal of the previous thread. If it's signaled, apparently return true. Then we should park and then interrupt the thread. And let's say if it's not signaled, let's ignore this part for now. Then we come here, compare and set the status to be signaled. And then we get to be signaled. So then we return false, we get out, come here. Basically this returns false, then we get out of this if statement, we come back to the loop. And when we come in again, we go to this method. Because we set it to signal before, given we assume another thread doesn't jump in and change it, now we return true. So this will ready to be parked. So notice at this stage, because we just parked the current thread, so we can have a look. We just parked the thread. So this operation will stop here, stop right in this line, until this thread is unparked. So then let's look at our release method. When we release, this thread will be unparked, given if its predecessor is the head. So let's have a look. Release. What does release do? Pretty simple. Just call tryRelease. That's usually a successful call because we just change the status. Then unpark successor doesn't do much. It basically changes the status. Notice we pass in the head node. Remember, we are passing in this node because the wait status of this node controls its next node, its successor. So if we have a look here, unpark successor, unpark, and this is the head. So basically we change the status, we change the flag, and if everything goes all right, nothing has been cancelled, we call unpark, which then comes back to the acquire method. To let's say AbstractQueued method, which, remember, we were parked here, we were suspended here, and when we call release, this basically comes back alive and get out in this loop. And if we are the thread whose predecessor is the node, is the head. So if we are this thread, which means we are good to go, then we update the head. What do? We change what we do. Again, we update the head node to be this one. Then nullify the reference to the thread. This becomes a new dummy node, a new head. And yeah, basically we return false. tryAcquire, we return false. Then in the acquire method, here we return false. Basically, because we return false, we get out of this if statement. Then we will acquire the lock successfully. That is a brief introduction of how AQS works. I hope you enjoyed it. Thank you.